Okay, finally there. Sorry, sorry. All right, so let's just do some examples from the end of 5.5, the last little bit, just to make sure that we're all on the same page, and it'll be good to warm up our math skills this morning, especially mine, since I'm like ADD here. Okay, let's see. So let's pull in our copy this, open this. We'll get there. We're getting there, guys. All right. There we go. We got our formula and we got our problems and we are good to go. All right. So this is just the last little section. So the last few problems, we want to use the half angle formula to determine the exact values of the sine, cosine, and tangent of the angle. So in number 40 and 42, those are just numeric values. So we can do that. So let's try number 44 and see how we get on number 44. So number 44, we have pi over 12, right? So what we want to do is use the half angle formula to determine the exact values of the sine, the cosine, and the tangent of the angle, right? So what we want to do, since we're using the half angle formulas, is if, for example, if we want to find what the sine of pi over 12 is what we're trying to find, right? And we want to use this half angle formula. What we're looking at is we're trying to figure out what value of u, like basically, what are we going to plug in for u? What is the let me explain this right. Pi over 12 is the halved value. So we want to know what is the value when it's basically doubled, right? So our u is actually what happens when this term is doubled. So that's because they've specifically told us to use the half angle formula. There's other ways to find the sine of pi over 12, but since in these questions they're asking us to use the half angle formula, we have to kind of think in our brain, we're using the half angle formula. That means I need to do, you know, a u over 2 or a theta over 2, however you want to think of that. So when I have the sine of pi over 12, I'm going to think of, okay, that's half of my value. So that would make my u be the double, which is pi over 6. Okay. So if I have the sine of pi over 12 and I know my u value is pi over 6, then if I use this half angle formula, I know that the sine of pi over 12 is plus or minus square root of 1 minus the cosine of u. So the cosine of pi over 6, all divided by 2. Okay, so now is where I bust out my unit circle, which I should have up on my screen, but I don't. So I can always search for it, right? Unit circle should be the first thing that comes up. Or you guys can tell me. So what I'm trying to find is what is my value, because I'm trying to find the exact values for the sine, cosine, and tangent. So I could plug in the sine of pi over 12 in my calculator. I don't know if that'll come up with an exact value or not. But I do know that if I can get the cosine of pi over 6, I know that's on my unit circle, so I can come up with an exact value. So where did I have that at? Back here, unit circle. Make it bigger. Oh, today. Okay, here we go. All right, so pi over 12 is not on my unit circle, but pi over 6 is on my unit circle, and I want to find, what do I want to find? I want to find the cosine. So the cosine is my x value. So the cosine of pi over 6 is square root of 3 over 2. Okay, so in here, I'm going to put 1 minus square root of 3 over 2 divided by 2. And then this is my magic paper that I can keep making bigger. All right. I'm going to change this to 2 over 2 minus the square root of 3 over 2 all over 2. Sorry, my handwriting's so messy. I still haven't figured out the pen thing yet on here. Okay, so then I keep going here, and I get, basically I have square root, right, of 2 minus the square root of 3 over 4. Sorry for the messy writing. And if I really want to simplify it, I can square root the top and the bottom separately, right? And I could say that this is plus or minus. I'll try to write it nicely. Square root of 2, or yeah, square root of 2 minus the square root of 3 over 2. So this would be the exact value of sine of pi over 12. So I don't know, I'm pretty sure if we go into Desmos or you use your TI calculator, you can try this for me. If I put in, just to kind of full circle here, here's good old Desmos. If I put in the sine of pi over 12, let's see what we get. It will surprise me. Yep, so we're just going to get some decimal value, right? Which should correspond to our radical value, which was the square root of 2 minus square root of 3. And the whole thing, nope, got to make sure you write it in there correctly, right? And the whole thing is divided by 2. So then we end up with the same value. Ta-da! All right, any questions about that? Besides the messiness? So then if I wanted to find the exact value of the cosine, right? The cosine is the exact same way, except that I mean, it's actually the exact same formula, right? Except we're going to use a plus here to figure out what the cosine of pi over 12 is. Which, spoiler alert, is just going to have the opposite sign. And then when we go to do the tangent, we're going to do the same thing. So basically, we're setting the value of u to be pi over 6. And then we're going to plug it in to this formula here. Okay. Does that make sense? Uh-oh, we just lost Aiden. Sure, I'd be happy to solve for tangent. All right, so let's do some tangent solving. I will try to write nicely. I'm trying to write with my finger on the screen is what I'm trying to do. So let's see here. Driving me crazy how messy it is. Okay. So the tangent of pi over 12 means that we're going to have a u value of pi over 6. So we have 1 minus the cosine. I think I'm going to need more room. Give me just a second here. Let's clear this off. There we go. Okay, back to the business here. We have 1 minus the cosine of pi over 6 over the sine of pi over 6 Oh, or we could write it in the other format. So we'll just leave it in that format. Or you could put the sine on the top and the cosine on the bottom. Either one is okay. So 1 minus the cosine of pi over 6. So this is 1 minus, and we already solved this, right? The cosine of pi over 6 is the square root of 3 over 2. Okay. And then we have the sine of pi over 6. So again, back to our unit circle. The sine of pi over 6 is going to be 1/2. All right. So we actually picked the right formula because this is nice and easy, right? So then I think what I'm going to do first is I'm going to flip the 1/2 off the bottom. So that means I'm actually going to multiply the top by 2 times 1 minus the square root of 3 over 2. Okay. Then I'm going to distribute my 2, and I end up with 2 minus the square root of 3. Okay. Does that make sense? Ish. Sure. Anytime. All right, so let's try, let's do number 48 just to make sure that we all kind of have it together, okay? So, let me clear this off. We'll do green. Sure, we'll do green today. All right, so in the last few exercises here, this kind of reminds me of exercises, if you did any of 5-5 yet. This is like 13 through 18. But instead of for the double angle formula, this is going to be for the half angle formula. Okay, so I just have 48 listed on here. We have the cosine of u equals 7 over 25, and that u is between 0 and pi over 2. So which quadrant does that put our angle in? If it's between 0 and pi over 2. First quadrant. That's right, Jennifer. Yep. Puts it in our first quadrant. Oh, I was so close to drawing a nice one. Okay, so we know that the cosine of u, so when we draw our angle here, right? This is our u. We know that the cosine of u is 7 over 25. Nope, I just drew that on there wrong. I know it's my x. Goes down here at the bottom. The picture was like, oh, that's where the 7 goes, but like when you see red, the name red and the color blue. Okay. So the cosine of u is 7 over 25. So what does that make the sine side, the y component? Well, we would use Pythagorean to figure it out, right? So we would say, let's call that y. It would say 7 squared plus y squared equals 25 squared. And I believe, let's double check in Desmos. It's going to be the square root of 25 squared minus 7 squared. I think it's 24. Yep, 24. So that's nice. They gave us some nice numbers, right? So we know that y over here equals 24. So this kind of problem with the quadrant and figuring out the x and the y component of the angle, we've done this several times, right? When we we did it in 5-4 and 5-5. Okay, so we have that now. So now what they want us to actually figure out is what is the sine of u divided by 2. Okay, so we know that the sine of u divided by 2 is equal to plus or minus 1 minus the cosine of u divided by 2. All right, and they've given us the cosine of u in our problem, right? They tell us the cosine of u is 7/25. So we're just going to plug that in, right? 1 minus 7 divided by 25 over 2. So then we have to do our, mathematical magic here. We're going to change 1 to 25 over 25 minus 7 over 25, still over 2, square root, plus or minus, and we end up with 18, right? 18 over 50. I did a couple simplifications there. So I subtracted 7 from 25 on the top, the numerator. And then I went ahead and took the denominator 25 and moved it down and multiplied by 2. So we have 18 over 50 square root. Thankfully, those both share a 2 in common, right? So I can say that this is plus or minus the square root of 9 over 25, which is plus or minus 3 over 5. So the sine of u over 2 is plus or minus 3 over 5. Cosine, again, we're going to do the same way, except we're going to have a plus there. And then tangent, just to kind of make sure we're full circle here, we'll do tangent in orange and kind of sneak it in here somewhere. Add to our page. Oops. Sorry, 3 over 5. Okay. The tangent, of u over 2, and we can pick either formula. So doesn't really matter. Since we already did the work of 1 minus the cosine of u, we can kind of duplicate our work, right? So let's do 1 minus cosine of u over the sine of u. 1 minus the cosine of u over the sine of u. Okay. We know that 1 minus the cosine of u is this, right? It's this or this, which it ends up being 18 over 25. I'm taking a little shortcut here, okay? Because we already did that work before. And then the sine of u is just going to be 24 over 25. And that's nice because my denominators cross out, right? My 25s. And then I'm left with 18 over 24, which simplifies to 3 over 4. So I think this kind of makes sense. You probably would expect this pattern since our sine was 3 over 5, or half. When we take half the angle and we take the sine, it's 3 over 5. So we would probably expect this to be a 3, 4, 5 triangle, right? And I think we did another problem earlier where it ended up with 3, 4, 5 as well. So that was nice and tidy. All right, any questions? Ready to tackle the rest of it? how I got the sine and the cosine. Oh, okay. Oh, for this last problem, how I kind of skipped some steps there. You're talking about this one. Is that right, Sarah? Okay. Yeah. All right. Let me go back. I was trying to be, yeah, I will show you. Maybe. All right. So, are you okay with the formula, right? We're just picking one of the two formulas. And then it's just how do we end up with the values? So, okay. Perfect. I'm glad you asked. Okay. So we have 1 minus the cosine of u. So what we're trying to find, they're asking in the problems, they want us to find the half angles, right? U over 2. But in the formula, we get to just use the regular cosine of u. So the cosine of u is, we're going to refer to this picture back up here. And actually, for the cosine of u, it's a given value. So they tell us that the cosine of u is 7 over 25, which is consistent with our picture, right? The cosine of u here would be 7 over 25. So we would put 7 over 25. And then the sine of u isn't given, but we figured it out based off of our drawing of the quadrant, right? So the sine of u is going to be our opposite over our hypotenuse. So the sine of u would be 24 over 25. And we base that off of the information they gave us originally about the cosine, and then the fact that it's in the first quadrant. We're able to figure out what the other sides are. So for the sine of u, then we would put in 24 over 25. So we're using the original values of u, right? We're using the original values of sine of u and cosine of u to find the half angle by plugging it in. And then in order to do them, does that make sense? Okay, awesome. Cool. Okay. So what I want to do today is just do a little intro to 6-1. We will probably not get done with 6-1. I did hand out the papers. 6-1 is interesting. So 6-1 and 6-2 kind of go along with chapter 5, and then the last 3 sections kind of go on their own. So I just wanted to give you kind of a little introduction to 6-1 today. We probably won't even take the whole time. Let me get my paper out here. I lost my first paper. So basically, up until this point, with all of our, here we go, here's my paper. Okay. Up until this point, with all of the work that we've done in chapter 4 and chapter 5, we, when sine, cosine, tangent, all the inverse, sine, cosine, tangent, are, all of our different theorems that we've used, all of the different information that we've used up to this point, we've pretty much run on the assumption that we're using a right angle triangle, or, a right triangle, one with 90 degrees, right? So what happens when we have a triangle that is not a right angle? So that's where chapter 6 kind of starts. So if you're thinking in your mind, like, how do I distinguish this before the test and all that? Everything basically up to the point of chapter 4 and chapter 5, using the unit circle, using the different identities, that's all based on the assumption that we have a right angle and a right triangle that we're working with, right? And what I mean by right angle is, so here, when we have our unit circle, right, we form a right angle with our sine and our cosine values, right? So that's where that right angle comes in on the unit circle, because any point on the unit circle, if I pull up my unit circle somewhere, any point on the unit circle, I wish I could draw on here really easily, forms a right angle. Okay, so if I draw my line, for example, to pi over 3, draw down here, try to draw nicely, right? We have our x component and our y component, and we have a right angle here, and this forms our triangle. So that's kind of, everything's based off of that. So in 6.1, they say, well, what happens if you don't have a triangle that is a right triangle? What do we do? Can we use the sine and cosine values at all to, glean any information? So what we can do is we have a couple of we have the law of sines and the law of cosines that we can actually use to determine the sides of a triangle. So let me pull up the law of sines here. I know you're like, great, but wait, there's more. Maybe I can get there. Here we go. Voila, the law of sines. Behold the law of sines. Okay, so this is what happens when we no longer have the restriction of having a right triangle. We can use the law of sines to help us determine the relationship between the angles in a triangle and the sides of a triangle. So I will read it to you here. It says, if ABC is a triangle with sides A, B, and C, then side A over the sine of angle A is equal to side B over the sine of angle B, which is equal to side C over the sine of angle C. So you can see there are two triangles here. They have an acute triangle. Remember, acute just means that all the angles are less than 90 degrees. And you can see that they've drawn the hypotenuse here. And we can go back and you can look at the proof, how they used all the information that we had in the last two chapters to kind of prove this. But basically, we have this relationship, and it's a proportion. So the side A over the angle A, the sine of angle A, is equal to the side B over the sine of side B. And that's also true for obtuse angles. So that is the law of sines. It's pretty cool that we can do something with non-right triangles, right? Just a side note, the law of sines can also be written in the reciprocal form, which makes sense, right? If just think about proportions. If you flip the proportions, the reciprocal is also true. All right. Now if you pull out your geometry brain for a second, the law of sines, this law of sines up here, is really good for triangles when you have angle, angle, side. So do you remember these problems back from geometry, or maybe you blocked geometry out? I don't know. But we had in geometry, right? We have different types of triangles where different information is given. So the law of sines works really, really well for triangles where you're given the angle, angle, side. So when you have two angles and you want a third, and you have two angles and a side, and you want to determine the rest of the angles and the sides in a triangle, this law of sines works really, really well. Okay. Where it gets a little bit trickier, it still works, and this is probably what we'll talk about on Monday. It gets a little bit trickier if you have side, side, angle. Okay, so law of sines works perfectly for angle, angle, side, because you have two angles in a triangle. So let's just draw any random triangle, right? So let me say that I tell you this is 60, and this is, I don't know, what do I want to call this? 40. Okay, and then I tell you that this is 10. Okay, so if you have a case where you have a triangle like this, law of sines is going to be your friends, and it will work perfectly. Okay, because it's really easy to determine what my third angle is, right? We remember, what do all the angles in a triangle add up to? 180, right? So I know just off the bat, without even having to do anything with the law of sines, I know that this is going to be 80 degrees, right? And then when I go to use my law of sines here, right? I have three of the four pieces of information, so I can just pop in really quickly and determine, let's call this B and C, what those sides are. So pretty easy to do. When you'll see when you get to side angle, it gets a little bit more tricky because, and that's on your paper, there could be multiple ways to draw your other two angles. But when you have two angles that are given, it's pretty much easy street. So we're going to do the easy one today, of course, on the call, right? And then we'll talk about the trickier case when we have side on Monday. Okay, so let's see. Let's do an example. So you see you get some more, this is when you have side. You get some more choices about how your triangle could be. But for right now, let's just ignore that and just pretend that all problems are angle, side, and it's nice and easy, right? All is well in the math world. Oh no, I think Aiden and Adam keep getting kicked off. I promise I'm not kicking them off. Okay, so let's go ahead. I think so number 2 is super easy. So if you look at number 2, just kind of take a glance at number 2. Right? What we know that angle A is 35 degrees and we know angle B is 55 degrees. So what does that make angle C? So 55 plus 35 is... Hey, Aiden, sorry you keep dropping off. I hope it's nothing on my end. So we were just looking at number 2. We know that angle A is 35. Okay. Angle B is 55. So what does that leave for angle C? It's got to be 90 degrees, right? 35 plus 55 is 90, so this has to be 90 degrees. So this is going to be a really easy one to solve. We can use the law of sine. I feel like when I'm saying law of sines, it sounds like law of sines to determine the other sides, right? But that's kind of our easy case. So let's go for a more difficult case. Let's go for number 6. So you see you have another triangle here. We have angle A and B are indicated on our chart, and we don't know what angle C is. So we need to figure out what angle C is, and then we also have to figure out what side A and side C are. Okay, so the first thing that let's kind of tackle is let's figure out what angle C is. And so that involves us remembering, what do minutes mean? So we know if we want to write this out, this is number 6, right? We know that the measure of angle A plus, this is back to geometry, the measure of angle B plus the measure of angle C equals 180 degrees. Okay, old school geometry, right? So the measure of angle A is 88 degrees and 35 minutes. 88 degrees and 35 minutes. So just remember, when you see the minutes, you can actually use the fact that you know how many, you know that minutes, conversions between minutes and seconds is 60. So when we have 35 minutes, that means 35 out of 60. Okay. Now, unfortunately, when you do 35 out of 60, it's a repeating decimal. So we can also put that down. It's 88.583 repeating. Okay. Then we have the measure of angle B is 22 and 45 over 60, right? Good old mixed fraction there. And then we have the measure of angle C. Now, I'll admit, when I did this, I didn't leave them in fraction form. I just made this 88 point, what did I make it? 88.583. And then this is 22.75. And then if you solve for C, I ended up with the measure of angle C equals about 60. It's 68.6 repeating. So I did 68.67 degrees. Okay, so that's back old school geometry skills, right? We know this angle over here is 68.67 degrees. Who said you don't use geometry again? That shouldn't be anything new, but the new part is that we have this law of sines that we can use to determine the other sides of our triangle. So we know that side A over the sine of angle A is equal to side B over the sine of angle B. So if I do a little fill in the blank here, right? Side A is my unknown. I don't know what A is, so A just stays by itself. The sine of A is going to be the sine of 88.583. Messy handwriting. And then B, side B, is the one that's opposite from angle B. And so that is 50.2 yards. Okay. Side B over the sine of angle B. So the sine of 22.45. No, yes, 0.75. So then how do you think we solve this? How do we solve for A when we have a proportion? We call it the butterfly in my house, but we just do cross multiply, right? So you can multiply this way. Oh, this paper is so ugly. And then you can multiply this way. And then we can solve for A, right? More paper. All right, so we get A times the sine. Sine of 22.75 equals 50.2 times the sine of 88.58. Okay, then I want to divide both sides by the sine of 22.75. And if you have your calculator there, number one, make sure that it is on degrees, right? So if I popped over to Desmos right now, Desmos defaults to radians, I believe. So that would not be good. So I need to do 50.2 times the sine of 88.583 divided by the sine of 22.75. And I just did what I said to make sure that you don't do, right? I left it in radians. There we go. So side A is about 129.8 yards. So I go back up here. I should have made my triangle bigger. This side is 129.8 yards. Okay. And then C, you're going to do the C the exact same way. My advice with finding side C. Yep. I did. Down here in my really messy handwriting. So we have the 50 yards times the 88.5 divided by 22.75. Oh, did I leave it out in Desmos? Let's see. I think it's, yeah. So 50 times the sine of 88.5 divided by the sine of 22.75. Cool. Oh, it needed to be divided. Oh, yeah, it's just the way that it's written. I think Desmos would actually, let's see if I put it into the top. You mean, I see what you're saying. I'm multiplying it twice. You'll actually end up the same way just because we're just breaking apart the multiplication and division. But I'm glad that you checked that because sometimes that does affect it. Yeah, good question. All right, where are we in this big mess of words? Here we go. All right, so then when you go to find side C, because we found, I know it's very messy, but we have found the angle C, right? And we've found side A. My recommendation to you is to always use the law of sines and use the terms that are given to you to determine other things. So for me personally, I wouldn't go, you could do it, it would work, right? But I wouldn't use A sine of A and make that equal to C over sine of C. Although this is true, because I just found the value of A, and in case I made an error in my calculation, I would stick with C over the sine of C equals B over the sine of B. I would stick with this proportion only because angle B and side B are given. So I know that if I made a calculation error, it doesn't carry over into both, both calculations. If that makes sense. So if we go to find side C, wow, this is messy. If we go to find side C, we can do that. So we have side C and then the sine of angle C. So angle C is 68.67, right? Okay. And then again, I'm going to go ahead and reference that to B because B is our values that I've been given. So 50.2 yards over the sine of 22.75. So then when I solve for C, again, cross multiply, I'm going to end up pretty much with the same formula. So I'm going to end up with C equals 50.2 times the sine of 68.67 over the sine of 22.75. Okay, so I can go back to Desmos. And I have almost everything in there except this angle has changed, right? This is now 67.67. So C is 120.1 yards. See up here, if we go back up here, this side is 120.1 yards. And that is a big mess, so I apologize. I don't like my math to be that messy, but someday I'll figure out how to draw on my screen. So that's how you use the law of sines. So if you're really feeling like you're good and you want to work on this, you could definitely do any of the problems where you have two angles and one side given. So for example, number 10, and I know this is not the odd answers, but number 10 has, they're giving you two angles and one side. Where we haven't talked about the case yet, and if you want to figure it out, you're welcome to, but we haven't talked about the case is, what if they give me one angle and two sides? Because there can be more than one solution. So we'll talk about that on Monday. I think it's just kind of a good intro to what we'll be starting out next. All right, so we'll wrap up with that today. Thank you guys for coming. Your homework will not be due on Monday, so it'll be due next Monday. I'll give you till the following Monday. If you want to turn it in this Monday, you can. After my calls today, I'll send out your Chapter 5 test, so then you'll have 2 weeks to complete that. So I'll put the due date when I send out the email on that. If you have any questions, let me know. Thanks for coming today, guys. I hope you have a good day. Hope everybody stays healthy, and I'll see you on Monday. Thanks, guys. Bye.